super, super excited for the next talk, actually, as this touches upon things from my former life as a cognitive scientist. We're going to have Pedro Lopes here from the Hasso-Plattner Institute, next door, kind of, right? Did you have like a long commute this morning? Or you
This morning, yes, but normally I wouldn't. But I wasn't at the institute today.
All right. And he's going to tell us about research that he's doing. So Pedro's background is in computer science. He's right now a PhD student at the HPI. And he's also a background in more artistic things, though, music, you said. And his current work is exploring something that lacks VR so far. It is taking something that is really important about VR, this embodied aspect, this thing that you can actually bring your body, move naturally in VR, and is looking at something that is missing on that equation, because so far VR is really great at having this embodied input, but there's no output. There's no proprioceptive feedback that you get. And Pedro's work is using electronic muscle stimulation to close exactly that gap and to let you really feel VR. So with that, I'm going to hand over to you and let us know when we can finally touch stuff.
Thank you. All right, so you got to switch your gears a little bit into the research mode. The things I'm going to show you are the research I did at HPI for the last 5 years with my advisor, Professor Patrick Blotter. And so these are not products, but these might be things that impact the products that we're going to see maybe in 10, 20 years in VR and other realities too. So let me start by showing you a little video that we did of a VR project that is trying to simulate walls. So this is perhaps one of the hardest things to simulate in VR right now, right? You put your headset on, you see beautiful graphics, but you just can walk through the door, you can even hurt yourself, you can go out of the tracking volume, you name what can happen. So we're trying to bring physicality, but we're also trying to kind of go for the hardest challenge. Walls, you know, heavy stuff, physical forces, how can we feel all of these things? And so, if you believe in me, what we were doing here was that we were electrically stimulating the user's muscles. This is the same thing that you go to the doctor, and the doctor might give you a rehabilitation device that sends tiny electrical impulses into your muscles, and that causes your muscles to move involuntarily. And so the devices that I'm going to show you for VR and for other purposes sometimes take over control of your body for a split second to give you feedback, to give you forces. And if you couple this with what you see in VR, this feels like some force is coming from the virtual world. And so this is what you saw in this video with my colleague Sijing that was going through this VR world. Now, I'm doing research in human-computer interaction. It's a little bit broader than VR, and VR is just one part of it. For you to understand a little bit better why I'm doing all these things and why am I sticking electrodes into people's muscles, let me tell you a little bit of a story of where we are right now in terms of the size of our computers, right? So we are kind of between the land of mobile devices, things we have in our pockets, which are really interesting, but are a little bit like an external device. This is my mobile phone over there in the small circle, and this is me, right? Mobile phone is an external device to you. It's very easy to you to tell the difference between you and the device. The device is external. Now, if you think for a second, like people in my field about 20 years ago said, oh, why don't we like put this here and call it a smartwatch? That was an interesting take. You know, the device can now go with you at all the time. It's very similar to what happened with VR headsets, right? It's a display with you all the time. It's a wearable. You wear it. But still, it's kind of easy to tell the difference between the device and you. There's a boundary. You know, the hardware of the phone or the hardware of the smartwatch or the hardware of the headset is entirely individual. It's all electronics. And most people in my field would say like, well, the next step is going to be this one, right? If the device is getting smaller and the device is getting inside of you, then we're going to implant devices. And turns out, and maybe of you, some of you even have implanted devices. Insulin pumps, pacemakers, that sort of thing. And it's a great device because it's functional. It talks to a part of your body that needs help, an organ, your heart with a pacemaker. One of the things that I'm trying to say in my talk is that this might actually not be the next step. The next step might be devices that overlap with your body. Devices in which you don't know really who's the device and what's the user because the device might actually use part of your own body to function, like the electrical muscle stimulation devices that I use, right? So here's one that I'll show you later This is a person in VR. This is my colleague Xijing, and he's actually feeling the weight of a cube. So the cube is virtual, but he's grabbing onto it, and he's feeling that it's heavy. The way we're doing it is with this device, right? The electrical muscle stimulation, but you can't say that the device is only technical hardware because the muscles are part of the device. So it overlaps with the user's body. And so let me show you a few projects that I did throughout my PhD in this space. And I kind of worked on 2 different tracks. This one is really kind of where we are here at VR Now, but I'll show you a little bit of this as well to give you some context. So let me talk a little bit about the idea of using electrical muscle stimulation, stimulate people's muscles to create forces in VR, so towards immersion. The first thing that I did in 2013 when I joined HPI was to build such a device. It's a really simple device. It sits on the back of a smartphone, and you can see what its effect is on somebody's arms. I click on a button and the arms are controlled. So this computer can control for a split second, can take over somebody's muscles. So you put that on the back of the smartphone, and what you have now, it's very simple, but the idea is that you have a smartphone that has forces as output, which is something we don't have, right? By means of the muscle stimulation, the electrodes on my muscles, it can kind of force me to go left or right. So if I'm flying a little airplane against the wind, when that wind force comes, my arms move involuntarily to the right, and I have to force against it with my other arm. So there's kind of me fighting my own self. And you feel like it's force feedback. So you feel like you're resisting a force. Obviously, that force is yourself. So what we did in that project, which we called muscle propelled force feedback, was to realize, great, we can do forces in video games. And we can do them, and people will perceive like they're fighting a force. But of course, the longer we keep on the stimulation going, the more opportunities we let people to understand what's really happening. They'll be like, oh, it's my own muscle that I'm fighting, and so forth. So we thought, well, let's launch another test balloon to see how realistic could we make a situation that doesn't even allow people to understand where the force is coming from. We call that project Impacto. And the idea on Impacto is to simulate impact sensations in VR, stuff hitting you. So what you see here is my colleague Xijing. He's boxing in VR. This is something that we showed at Amaze a few years ago. And he's feeling every single punch from this boxing simulation. And so we thought, okay, what's a punch comprised of? It's comprised of 2 things, something that touches you and the force of the mass of that object hitting you. That force you feel on your muscles, okay? And so we thought, let's create 2 little tactile things. So one is just a solenoid that slaps you, and the other one is the muscle stimulation that just moves your arm backwards. Independent systems. Now when you put them together, it creates an illusion in your brain that something hit you, that something had sufficient mass, and your arm flies backwards. And so, of course, when you put that with the visuals in VR, what Xijing sees and feels is a punch. And you can start putting these solenoids everywhere to give other sensations. Like now he has a sensation, he's also punching back. And we had fun. We put it all over the body. So, I mean, the bracelet, the Impacto bracelet, once you open it up, it's nothing really complicated. It's a Bluetooth unit to talk to the computer who's running Unity and doing the simulations, as you would expect. There's a microcontroller that essentially is controlling the electrical muscle stimulator. It's the same thing that the doctor uses. This is a medical grade one, except instead of having the doctor fiddle with the knobs of the intensity, we have the microprocessor doing that in real time. You have the batteries, and we have this solenoid, this electromechanical component that moves, right, and slaps your skin. And we have the electrodes that deliver the electrical muscle stimulation impulses to your muscles. It makes your muscles move. In that case, you saw the biceps moving, right? And so if you think this component, which is really big right now and could be miniaturized, is the one that is doing all the illusion and doing all the force, well, it's not true. Here's like a setup that I have to measure how strong things are. And when I hit that little slapping thing on your skin, it does 200 grams of force. That's something like that. Really, really, really weak. So truly, what's doing the big sensation and the big force, what's really moving you, is the electrical muscle stimulation. So the other component, you can even miniaturize further. All right, so we kind of had fun with the project, and we started putting it all over the body. I'm going to show you just a few selected things, not all of them, but they're all on YouTube if you want to see the videos. This is one of my favorite because we had the chance to put the bracelet on someone's foot. So what you see here is that it gives sensations to your toes, like something is touching you here, and the muscle stimulation, which is on the leg, makes your foot go downwards, okay? So what you see here is CJ kind of juggling a football, and he's not very good at football, by the way. You can see he's holding the wall. But he's a martial artist. And so the next one, and we did things like martial arts where CJ is really good at. The next thing we did was, okay, can we export this idea of forces to even objects that we're holding on to? And so what you're going to see here is a baseball application in which you're hitting a virtual ball, but you're holding onto something real that makes you feel like you're holding onto a bat. Now, obviously, you don't have to hold onto a bat because it's VR. So you just need to hold on to something. That something is just a handle. It's a prop. And the solenoid is on that prop, and it hits the prop, so you feel the vibrations as that vibrates. Now, you still need that big force feedback, right? So we put the electrodes on your muscles, and when your bat hits the virtual ball, your muscles fly backwards. And the whole thing combined makes you feel like you hit a virtual ball or a real ball. And so with these two test balloons, we kind of learned two things, right? One is we can represent continuous forces, like if something is pushing you, the wind force. And we can also represent really tiny impacts by just doing these really brief stimulation pulses, right? 200 milliseconds or 300 is what we did for Impacto. It's like you cannot even feel it. Your brain doesn't have time to realize truly what's happening. It just really quickly happens. So we put it all together and we created a longer session of VR, which we call VR Walls. It lasts about 10 minutes. And the kind of goals that we had here were to put it all together, make it a really encompassing experience, and as physical as possible. So we tried to do things that people haven't really figured out how to do in VR. One of them is how to hold something and feel that it's an object, feel that it has weight. And the other one is generate the sensation of walls. So here's the complete experience. There's these electrified walls that you've seen how we do it, right? It's the same trick as an Impacto. But there's also a button here. As he's pressing onto the button, he feels continuously force pulling backwards. So he feels like there's resistance, like there's a spring inside the button. He opens the door with the button, and there's these cannon shooting projectiles at him, which we will use the same trick as an Impacto to feel the hits. So he goes onto a portal, and there's another room. This room has a bunch of interactive objects he can drag around and pull. So you have these knobs on the wall, which you can slide. And as you slide them, we pull your shoulder against you, but we just pull it a little bit. And so it feels like friction, because you can still overcome the force, but there's a little bit of force. And to complete the puzzle, he must use these two buttons, which work like the button we've seen before, except they're tethered together. So it's like a pump. When he pushes one button inside, the muscle stimulation makes his other hand go out, and go in, and go out, so forth. So it's kind of a dialogue. He goes through the new portal. He gets to the third room where there's a bunch of interactive objects he can pick up and play with. So the first thing he can do is to feel the boundaries of the objects, right? If he puts his hands like that, he knows where the object starts and stops, because immediately his hands kind of stop in the air where the object walls are. He can also push the objects around and feel the friction as he drags them along. But more interesting, he can pick up this cube. And I think this is where our project becomes really interesting, because we're giving the sensation that it's heavy as well by pulling his muscles down all the time when he's holding onto an object, right? That's what happens when you pick up an object. You have to fight the gravity. Here you're fighting yourself. And so when we showed this project around, people used to say things like, oh, it's kind of heavy, and they would let go the object. And it was truly heavy. It's just they were not fighting gravity. They were fighting themselves. And this is the kind of project that gives you like really funny headlines in the media. Get a virtual punch, feel real impact, and hacking your muscles. I guess I was asking for that. More interesting is that we were able to export this into our peer group, but also at places like Amaze, and get people to try it. And every time we've shown it, we actually worked a little bit on it. When we show it at Kai, we felt like some things were not right, especially with the weight simulation. So next time at SIGGRAPH, the weight simulation was already a little bit better. So it's really nice to get feedback from people on these projects. Now, hopefully, sort of 10 minutes in the presentation, you should be asking yourselves, what is Pedro talking about? Why would we stick electrodes onto people's muscles? That is really strange. And so there is a kind of hidden benefit here, but maybe some of you already caught it. The truth is that, you know, VR did not start in the 2000s, much less with me, and much less even in the 90s. People have been working on VR since the 60s, but people have been trying to make VR physical since the 90s. The way they do it is by using mechanical systems, and the reason why we don't have them, why HTC doesn't sell one, is because they're huge, right? And you don't want to have this thing at home. Here's an example of a perfectly good one. This is a fantastic system called Exo UL7. It's being used in VR. And here's what it does. So it's really similar to what I've just shown you, right? So here's what the user would see. You see a ball. You can feel the gravity. You can play around. You can feel the resistance of the ball as you push it. You can feel the contact when you kind of hit the ball. This thing might even be faster and is probably more precise than my systems. The difference is that this thing is bolted to the wall. It weighs probably something like 1 ton, and it probably has 1 ton of batteries in the next room. So this thing is not going to go anywhere. And VR, as it is right now, as you buy it from HTC and Oculus, it's a mobile system that is really easy to set up in your home. Doesn't require to bolt an exoskeleton to the walls. So you see there's a mismatch, right? So a system like that is probably not going to hit mainstream VR, but a system like this is much smaller because essentially what I'm doing is I'm just reusing parts that are already there. I don't have to put an exoskeleton because luckily we have the skeleton. I don't have to use really heavy motors, which also don't shrink down in size because I'm just reusing the human muscles as motors, right? I'm just activating them with a control signal that is the electrical muscle stimulation. What is really interesting is that I also don't need an extremely big battery pack because we all eat a lot of stuff in the morning. It's called energy, carbs. And this thing here has a tiny battery, but that battery has nothing to do with powering the contraction. So when your muscle is moving, the energy is coming from your own internal reserves of energy, which is a perfect battery designed by nature. And this little battery here, just a go signal. It's a control signal that says muscles, do it now. And so the whole system is much smaller and more efficient. So it's a contribution in the sense that I'm proposing some other approach to miniaturize the hardware, just like it was said in the introduction, that allows us to feel body output in VR, to feel like something is really moving us, feel like there's things in there. Now, if you indulge me in 5 more minutes of insane muscle stimulation stuff, let me talk about the second line of my research, which is taking this out of VR and into a different context. So question here was, how can we miniaturize the hardware? But what if we just take the hardware as miniaturized and just say, like, what if we start representing information through poses of the body? So here we were not representing information. We were making things become realistic, right? If there's a cube, there's a cube. But here we can do the mappings that are not like direct. Here's a direct mapping. You should feel a cube, you feel a cube. What if we start going for arbitrary mappings? Just show you information. So let me show you the first project that we did. The first thing that we did was to represent one variable, so one piece of data, changing over time. And that as that data is going to change over time, my muscles are going to go up and down. This is me with less hair, by the way. So this is just for us to see what the mapping is. The system wants to represent information. Let's pretend it's how much time I have until the talk is over. And it just moves my muscles. Now, I can also move my muscles. The system can sense that. That's me inputting information. The system, again, can output more pieces of information, one variable changing over time, by moving my muscles up and down. And I can feel that. What is interesting is that you can see that I'm not looking at my hand, right? I don't have to look at my hand. I can just feel the information flowing. You already kind of caught that. The way it works is that I can move your hand by means of the muscle stimulation, but there's a little accelerometer in your finger that allows the system to know where your hand is posed. So that's just the same accelerometer you have inside your phone and knows the orientation of your phone. Now, the reason why I didn't have to look at my hand is the same reason why I can do things like this, and I don't have to look at my hand to know it's a 4 and so on. There's a system inside our body that you alluded to earlier. It's called the Proprioceptive System. It tells us how our body is organized in space. So this is a new type of interface because it's eye-free. I don't have to look at the display to see that it's at 50%. I just feel that my hand is in the middle. And so we've been kind of using and abusing this idea of transforming the user's hand into an interactive device. And I'm going to show you an example. This is a situation very similar to what's happening now. I'm giving a talk, and I want to look at the audience and not at the video. But I also want to know where that video is. I want to know if it's in the beginning or in the middle. So as the video plays, my hand moves upwards. Hand in the middle, video in the middle. If I push my hand down, video goes back. So it's kind of like one-to-one mapping with this idea of information flowing and my body moving. All right, that's not important. The bracelet is not that different from the one I've shown you before, right? 3D printed shells, smaller batteries this time, more Arduinos. The muscle stimulation controller, this is the thing that actuates your body. There's also a symmetric unit to sense what your muscles are doing. This is like the opposite of actuating your body, sensing your body. And there's the accelerometer that tells the system where your muscles are, right, in space. And so if you think of what was happening when I was controlling that video playback, what was happening is that me, the human, and the machine were sharing the same device, like the same joystick. And that joystick was my hand. We were sharing the same interactive device to talk to each other. Now, it could be that we would use different devices. So let's say that I would say, like, I take my right hand, and the system takes the left hand. And now we can kind of play a game together and kind of have a dialogue. And so this is Patrick, and he's playing this game. This is for children, that two people try to slap each other and the other one tries to avoid. It's called red hands in English. And so he's playing that alone. So the computer hand is trying to slap him, and he's trying to avoid, which, by the way, is incredibly hard because of reaction time. And so he's wearing the same devices you've seen before, except there's this little black bracelet here, which is a microphone. So this is just to make sure that this is actually a working game. So when his computer hand slaps the other hand and he cannot avoid, what happens is that we hear this little sound. Oops, sorry about that. We hear this little sound in the microphone, so we can score how many times he has lost a point or not. So it's kind of a full game. And so in the next project, we decided to, well, maybe if we can represent information through poses of the body, then we can export that into all the objects around us. So we started toying with the idea of extending the affordance of an object. So if you don't know what affordance is, it's just how objects communicate to you what you can do with them. I know that I can hold this microphone without having to think too much about it, because the microphone has, for instance, a small grasping radius, right? If it's not like that. If it's like that, I wouldn't grab it with one hand. So objects kind of automatically communicate to you what you should do. Same with this spray can, right? You know you can grasp it, you see a button on top, you know you can press it. But there's a problem if you ever use the spray can, you probably forgot that you also have to shake it before you use it. And so we thought, well, can we put muscle stimulation on people and try to help them learn how to use tools that maybe they haven't seen before or they don't know how to use before? So we extend the affordance of the object. So what you're going to see is video from a user study, so you'll just hear what people can say about it.
Yeah, that was cool. I totally would have forgot to shake it.
I need to shake it.
And you can see how the muscle stimulation starts to shake. It's kind of a slower shake, and then when people really put their motion into it, it's more of a functional shake. All right, you know what this is going. There's plenty of people shaking. I'm gonna skip to the last one. This is all on YouTube. I'm gonna skip to the last one, which is my favorite. Here, we said to people, why don't you have a drink from this? I hope you can see that this is a cup. Go ahead and drink some water.
Okay, I feel like it doesn't want me to touch the water. Not at all. Maybe I should need to grab the handle. Yeah, I think I need to grab the handle.
It's too hot.
It's not cool to grab the thing, but the handle is okay, no matter how I grab.
But it allowed me to grab it on the much colder.
So this
handle.
person got it particularly right. What's happening here is that we're kind of envisioning a system, doesn't exist, this is a prototype, that would have a temperature sensor inside. And indeed, if the content is too hot, and it was too hot in this case, it tries to help you and say, you know, protect you. Don't grab it like this, like a cup, because it still affords to be grabbed like a glass. And says, why don't you grab it only over there? And then later, if the contents get cold, the system would dynamically readjust the possibilities and allow you to do both things. All right, one last project before we say goodbye. So the next one is Muscle Blotter, and it's a little simple. It's a little harder to see what it's doing, but it's very simple to explain. So if you think of all the 5 projects I've shown you before, there's a little aspect of them that maybe some of you already figured out, is that once the system is going, so let's say that I'm feeling where the video is at, you know, I know what's happening. Okay, the video's on the top, the video's in the middle, the video's in the start. But once it turns off, there's no way I can make sense of the information because the information was living in my proprioceptive system, was living in my muscle memory, quotes, because I don't like that word too much. And so for us to make sense of information, we need to be able to visualize it. We need a trace of it. So what it did, Muscle Plotter, was to create a system that allows for more complicated things than just, you know, slapping or seeing where the video is at. And we did that by kind of digitizing, leaving a trace of the information of the muscle stimulation with a pen. It's a very simple approach. So what you see here in Muscle Plotter is that there's 2 car designers, and they're doing what all car designers in the world do. They're trying to figure out which of these 2 cars is the most aerodynamic. Now, because they have Muscle Plotter, which is a little pen and a muscle stimulation unit that digitizes everything they write, they can figure that out without having to go to the computer. So let's see what they're up to. So what you see here is that when the person writes wind tunnel 10, it sends a command to the computer, which is in the background, and says, can you simulate that car in a wind tunnel simulator? And now when the person does this motion, the system turns the wrist left and right to show the data from that simulation. So this is not the person drawing, this is a simulation output being drawn by controlling the user's muscles to draw that. Now, they realize that, wow, that looks actually really promising. This is a nice profile in there. Let's look at the tail profile. Let's look at the winds cutting the tail of the car. So they draw a plot, but the system takes over and draws the data of the plot. This is something you don't know. You don't know how the wind profile is going to look like there. And you know, this video is fast forwarded because this takes 10 minutes. These people are trying to solve their problem in 10 minutes. They do the same for the other car. They're trying to compare. And turns out that, wow, less negative wind. Negative wind means turbulence. Oh, that's probably a better car. Let's ask the system what is the drag coefficient, which means how much the car is being slowed down as it moves forwards. And turns out that this is indeed a better car. Now, what's interesting is that did all of this without going to the computer, and the pen and the paper became their computer by their muscles becoming a plotter to represent information. All right, so there's more of that. I'll skip through the videos. You can watch them on YouTube. This one is my favorite. It's also drawing plots. All right, so to finish it off, one of the things that I try to do in my PhD to not be, too much preoccupied with just working on my own systems and debugging why the 3D printer is not working or something like that, is to give this to the hands of the community in VR. So we've done this contest at the WIST conference, which is one of the best conferences kind of in my field, and we gave an electrical muscle stimulation kit that is pretty easy to use to a lot of students, 18 student teams, and they came up with their own projects. And I'll just show you some of my favorites because there's no time for everything. So I'll just show you 2 and then I'll end my talk. This is a really beautiful one. So there's a leap motion here. I don't know if you know what it is. It's a sensor that can track your hand. So this person is playing rock, paper, scissors with their own bodies. So over here, you kind of choose paper, and the computer with the stimulation is going to choose rock over here. So the computer lost in this case. And this is my advisor, Patrick. He's trying a VR project where you see content that is of emotional nature, kind of like a happy stuff. And with the electrodes here, it makes you smile when you see that content of emotional nature, which I find kind of cool. So it's kind of emotion feed forward. All right. What I think is really important, just to conclude, is this part. It's like what happens when we start overlapping an interactive system with the user's body. And the technical contribution that I've shown you that I think it's important here for VR now is that maybe in the future, we don't have to walk around with huge exoskeletons in our VR systems. We can maybe walk around with small wearables that talk to our muscles directly. And that's it. Thank you for listening.